So my name is Lennon and I'm an engineer and I work in various types of engineering, but mainly extreme and unusual environments. So at school my favourite subject I would say was maths, and secondly applied maths or further maths, and science subjects I quite enjoyed as well. But what might seem unusual, I enjoyed and still enjoy history. So I started out studying civil engineering and found I was very interested in analysis, studied that at graduate level, later at research level, and that led me further into analysis and into the job I do now. We use matrices all the time. In fact, all of our problems are set up as matrix equations in the software itself. It's quite important to understand some of the principles underlying these matrix equations and how they expand rapidly and how the problem expands rapidly if people don't model it correctly. Again, it's worth spending time sitting down, thinking hard about what type of model somebody is building for an analysis before rushing ahead to the software. The software is only there as a tool at the end of the day, and ultimately it's up to the engineering analyst to choose what to do and to do it correctly and sensibly. It is many years ago. I'll say I remember the moment, I remember the general time I was learning about matrices, and yes, I did wonder what all of these matrix solutions would mean at the end. Now I know. An equation for physics that we use all the time is quite a simple one that's fundamental in dynamics. It relates forces to the effect of mass, the effect of damping, and the effect of stiffness. Fundamentally, for the type of physics I do, there is always some form of stiffness in there, some form of damping, and some form of inertia that is related to mass. If I try to separate out the problem by just remembering those components of the equation, usually I can find what's really driving the system, and that tells me what to focus on, what to focus my efforts on in solving and getting it correct. The most interesting thing is trying to solve problems, particularly difficult problems and ones that are not obvious at first. So an example of one of those problems would be if somebody comes to me looking to install something in the sea, or perhaps analyze something under the sea, and how can it be done? And I sit there and work and spend a lot of time doing some hard thinking about how it can be done, and then gradually build up the problem and then build up the solution. So it will begin by thinking about what somebody has told me, and then thinking hard and analysing what they've told me from what they've told me and what they actually want, which don't always match up, and trying to then understand why they're trying to do what they're trying to do. Eventually, I start delving more and more into the what and why questions, and that brings me on to how. I start devising solutions and then choose one of those solutions. Finally, I implement that in an analysis package, and in some mathematics and engineering type equations, and then finally produce something that can help the client to do what they actually want to do. Well, the work itself is for difficult and dangerous environments. Thankfully, I can do it all in a nice, dry, calm office, which is very important because then I can think when I'm not under immense pressure myself. So a typical environment might be deep sea. I've done analysis down to 3 kilometers deep, which the pressures are immense. I've done analysis for systems that are at 1,000 atmospheres of pressure, which is very, very high and will explode rather dramatically and catastrophically if something goes wrong. At these sort of depths, at these sort of pressures, the engineering becomes difficult. It's not very straightforward anymore, and many of the simplifications no longer apply. So I have to think about that. Most of my work these days is actually in the thinking and reviewing other people's work, rather than doing the detailed equations themselves, or rather than driving the software that does the analysis, although I'm an expert in that as well and can do so if required. So at school the subjects will be essentially maths and physics would be the 2 main ones. At university it would be a degree in something like engineering, physics or maths. There's no need to be too specific about which type of engineering, mechanical, aeronautical, civil, naval architecture, all of those apply. Mainly what's important is having a good solid base in that and understanding the key principles rather than too many of the details.